let's take a look at the atom. So if you look at the atom, there's three subatomic particles: the proton, the neutron, and electrons. And if you look at them, the protons and electrons have charges. The charge of the proton is positive, and the charge of the electron is negative. The magnitude or size of the positive charge and the size of the negative charge is the same. They're opposite in charge, but they're the same. So if I have one proton and one electron and I put them together, their charges are going to cancel each other out, and it's going to result in a neutral charge. If I have more positive charges than I do negative charges, it's going to be positive. So in other words, if I have more protons than electrons, the atom will have a positive charge. If I have an atom that has more negative or more electrons than positive protons, it will be negative. So if you look at the atom, you notice that in this drawing that I made, the electrons are on the outside of the atom. All right. So here you have one here, and you have one here, and the protons and neutrons are in the center of the atom. The center of the atom is the nucleus. So the nucleus has the positive protons and the neutrons. The overall charge of the nucleus is positive, and that's actually what holds the atom together. Is that negative charge electrons is attracted to the positive charge of the nucleus, and that's actually where most of the mass of the atom is. Actually, nearly all the mass of an atom is located in the nucleus. The electrons have a very, very small mass, about 1/2000th that of the protons and neutrons. The mass of the neutrons and protons are nearly the same. Okay, so if you look at atoms, right, and atoms of an element can form isotopes. And what an isotope is that if you look at any element, the number of neutrons may vary from one atom of that element to another. And the neutrons is the only thing that varies. If you change the number of protons, it's no longer the same element. So as an example, I put carbon down here. If you have a carbon atom, there's a potential for at least 3 different isotopes. And in those 3 different isotopes, you could find 6 neutrons, 7 neutrons, or 8 neutrons. And if you look at, since the mass of a proton is very close, and their mass is expressed as atomic mass unit. So protons and neutrons, so if you look at protons and neutrons, their mass can be expressed as atomic mass units, which abbreviation is AMU. So I gave an example. If you look at the 3 common isotopes for carbon, you have carbon-12, carbon-13, and carbon-14. So this number here, right, that tells you the atomic mass units of that isotope. So if you look at carbon-12, there's 6 protons and 6 neutrons. If you add them together, it's 12. So there are 12 atomic mass units. Because protons and neutrons, their mass is an atomic mass unit. So a carbon-12 atom, right, so that's an isotope, it has 6 protons and 6 neutrons. And its mass is 12 atomic mass units. Carbon-13, on the other hand, has six protons. So you notice in each one of these, the number of protons does not change if I added more protons or subtracted the protons, it no longer would be carbon. But this one, carbon-13, you have 7 neutrons and 6 electrons. So if it's a neutral atom, the number of electrons and protons is going to be the same. So a carbon-13 atom has 6 protons and 7 neutrons. And then a carbon-14 atom, it has 6 protons and 8 neutrons, and 6 electrons. And so its mass is 14 atomic mass units. So another way of thinking about this is that of these 3 isotopes, carbon-12 is the lightest and carbon-14 is the heaviest. Now, ion, this is another term we'll see describing elements. An ion is a charged particle. And we'll talk more about that later on. But what you need to know now is that if the number of electrons or protons is the same, an atom will not have a charge. However, if the number of protons is more than electrons, it will have a positive charge. And that's called a cation. So a cation is a positive ion. An anion is a negative ion. And that's where you have less protons than electrons. In other words, there's more electrons than protons. So the net charge is a negative. So if you look at chemical reactions, a chemical reaction between a metal and a non-metal, what you'll see is that the metal is positive and the non-metal is negative. So actually what you'll see is that forms an ionic bond between the two of them, which we'll discuss in more detail later on. Ions can form, or I should say, you can see ions as monoatomic ions. So the prefix mono means one. So a monoatomic ion is an ion that is composed of one atom. And there's a list of common monatomic ions in the notes. So I would take a look at those. You probably would need to know those. Actually, will need to be able to use those to form bonding molecules on tests and quizzes. A polyatomic ion, on the other hand, is 2 or more atoms that are bonded together, and they have a positive or negative charge. So a polyatomic ion is a group of atoms that are bonded together covalently. However, the group together overall has a net positive or net negative charge. So a polyatomic ion can be a cation if it's positive in charge, or an anion if it has a negative charge. And when we do bonding, we'll see bonding, ionic bonding specifically. What you'll see is that the polyatomic ion, when we're trying to figure out how many you need to equilibrate the charge in a molecule, you would treat that as a unit. Now, when we look at the periodic table can actually tell us a lot about what to expect as far as ionic or covalent bonding and whether something's going to have a charge or not. But first, we need to look at some terms. If you look at the periodic table, the elements are arranged according to the atomic number. And it's organized in periods, which are if you look at the group, it's a column, the rows going across. Right, each one of these rows is a period, and the groups are going up and down. So they are these vertical columns. So if you look at the groups, they're also called families. The elements that are found all the elements found in the same group, they have very similar properties. So for instance, group 17 that's over here, these elements are very reactive, and they all have 7 valence electrons. However, if you look down here, actually let's go to group 18. Group 18, which is right next to this, group 18 has 8 valence electrons. They're very non-reactive. They don't take part in chemical reactions. They're very stable. Or if you go back to 17, there are 7 valence electrons. They want to have more and more valence electron to achieve the octet, or 8 valence electrons to form a stable electron configuration. In other words, they want to be like group 18. Group 18 is referred to as the noble gases. Group 17 are called the halogens. Now, if you look at the group number, and specifically I'm going to look at 1 and 2, and 13 through 18. Okay? All the elements in group 1 have one valence electron. So what's the valence electron? That's the number of the outermost electrons. So if you look at hydrogen, lithium, sodium, potassium, right, all these in group 1, they all have one valence electron. If you go to group 2, they all have two valence electrons. So if you look at magnesium, Mg, right, it has two valence electrons. And groups 1 and 2, they're metals. They have a tendency to lose their valence electrons when they bond. So they're going to form positive ions. If we go over to groups 13 through 18, these are the nonmetals for the most part. If you want to figure out the number of valence electrons in groups 13 through 18, subtract 10 from the group number, and that's the number of valence electrons they have. So if you look at group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5. Group 16 has 6. Group 17 has 7. And group 18 has 8 valence electrons. And that's important because if you look at, except for the noble gases, groups 13 through 17, they want to achieve 8 valence electrons, the octet rule. And they'll take part in bonding to do that. And something to note as well is that if you look at the periods, which are these rows going across, they're called periods because they refer to the periodic property. In other words, a repeating pattern of the properties as you go across from left to right. So if I go, let's start here in row 4. If you go across row 4, you're going to go through these metals, these transitional metals, and then these non-metals, including the halogens that we mentioned, as well as the noble gases. And then if you go to the next one, row 5, period 5, you're going to go through the same pattern. So it's a repeating pattern. It's periodic. That's why it's called the periodic table. All right, chemical bonding. Atoms take part in chemical bonding so they can achieve a full valence shell. And I mentioned this term before, but octet rule. The octet rule is what most atoms, not all, most atoms are trying to achieve. They want to achieve 8 valence electrons. Why do they want to do that? That's the most stable electron configuration for valence electrons. And if an atom achieves that, they have the lowest potential energy that they can have, and they're much more stable. So again, valence electrons are electrons that are the outermost electrons. They are the electrons of atoms that take part in bonding. The electrons that are below the valence shell, they generally do not take part in bonding. Ionic bonds are bonds that occur through the mutual attraction of oppositely charged ions. And when we look at ionic bonding, you may recall from talking about ionic bonding probably in high school or other classes, that in ionic bonding there's a transfer of electrons between atoms. Why did they do that? Because you'll transfer electrons between atoms to achieve the octet rule. In other words, you're going to fill the valence shell. And when we do that, atoms that lose an electron have a positive charge, and atoms that gain electrons have a negative charge. And the result is two oppositely charged ions, a cation and an anion, and then they're attracted together and holds together. That's an ionic bond. Covalent bond, on the other hand, is a bond that occurs between atoms where there's a mutual attraction or sharing of valence electrons between the atoms. Now, what determines whether you have a bond that's either ionic bond or covalent bond? It's the electronegativity of the atoms taking part in the bonding. So if you look at the electronegativity, that's a measure of how strongly an atom attracts electrons. And it's a scale that goes from 0 up to 4. The higher the number, the stronger the electronegativity. So 0, there's no difference in the electronegativity between atoms. But if you look at 4, that's the highest electronegativity that any element can have. Fluorine is the only one that has a electronegativity of 4. When the difference in electronegativity between bonding atoms is 0 up to 1.7, a covalent bond forms. When the difference in electronegativities between bonding atoms is 1.7 up to 3.3, an ionic bond will form. So what does that mean? Well, we'll look at some examples, but let's first look at covalent bonding. There's two types of covalent bonding that can occur. If I have a polar covalent bond, that means there's an unequal sharing of valence electrons between atoms. In a non-polar covalent bonding, there's an equal sharing of valence electrons between bonding atoms. Okay, so chemical reactions, if you look at chemical reactions, in a chemical reaction, you have reactants and products. And let's look at an ionic bond. All right, so here what I did is I wrote lithium and chlorine. So lithium has a positive 1 charge and chlorine has a negative 1 charge. All right, if it's 1, then you don't have to put a number there. When I bond a lithium and a chlorine together, their opposite charges cancel each other out. So the net result is you don't have a charge. The lithium chloride is actually a neutral. So how do I know how many of each I want to do? Well, let's look at magnesium. So magnesium has a positive 2 charge. Chlorine has a negative 1 charge. So how do I know when I bond them together how many I want to have? Well, I need to equal out the charges. So you can see magnesium has a positive 2 charge and chlorine has a negative 1 charge. So in order to cancel out the charges of each other, I have to have the same number of charges. So in other words, I have to have, if I have 1 magnesium, I need to have 2 chlorines to equal the charges. All right, and I have magnesium chloride, MgCl2. One way of doing this to determine it is we can cross the charges and treat the charges as the number of atoms that I have to have of that element. So if I take the magnesium here and I use that as the subscript for the chlorine, right, and the charge 1 charge for the chlorine, and I use that as the number of magnesium, that tells me how many I need to have. So I would have MgCl2. Why? Because the positive charge of the magnesium was 2 plus, and the chlorine was negative. So I have to have 2 chlorine, right, which equals 2 negative charges to cancel out the 2 positive charges of the magnesium. So if I have another atom, let's look at chromium. Chromium has a couple of different charges it can have, but let's say it's chrome 6 plus. And then we bond that with chlorine. I'm going to take the charges and treat that as a number that I'm going to use for the number of the element. So I'm going to have 6 chlorines, right, and just 1 chromium. I don't need to, if it's 1, I don't need to put a subscript of 1 because it's understood. So we have chromium chloride, or 1 chromium and 6 chlorines. So the sum of the charges should equal 0, right? So if I have 1 chromium, which has a plus 6, and six chlorines, which have -6 if I add them all together. Those are going to cancel out, and I'm going to end up with a neutral charge. That's what I want to have. So the sum of the charges should equal 0. All right. Now, how about if we have chrome 6 and the sulfide SO4 2 negative. So this is a polyatomic ion. I'm going to treat this as a group, right? So when I figure it out, so this is the SO4 is going to stay together. So the charge is going to cross, and what I'm going to end with is Cr2 6, SO4 6. In other words, this is saying there's 6 SO4s and 2 Crs. One of the rules of writing formulas is that my subscripts, so these number here, those have to have the lowest common denominator. In other words, if I can divide it by itself, I need to be able to, I need to make them smaller. So Cr2 and SO4 6. If I can divide both sides by 2, and what I end up is I'm going to have Cr SO4 3. In other words, there's going to be 3 SO4s, just 1 Cr. Okay, so you always want to make sure that's the lowest common denominator. Covalent bonding. In covalent bonding, if you recall, there's a sharing of valence electrons. Why? By sharing valence electrons, you can achieve the octet rule. In other words, you want to fill the shell. Now, I put on here carbon and 4 hydrogens bonded to the carbon. If you notice, hydrogen is an exception to the rule. They just want to have 2 valence electrons because they'll fill the shell. The carbon wants to have 8. So if you look at carbon itself, when it's not bonded, it has 1, 2, 3, 4 valence electrons. It wants to achieve 8. So what it's going to do is it's going to bond with these hydrogens, and in doing so, if you look at the difference in charge between the difference in electronegativity between the hydrogens and carbons, it's less than 1.7. So you're going to have a covalent bond that occurs. If the difference in electronegativities between the carbon and hydrogen was greater than 1.7, then you have an ionic bond that occurs, but it's less. And when we look at it, you'll see that the hydrogens, right, their valence electron. So what I'm going to do is I'm going to make hydrogen, I'm going to make it in red. Right, its valence electron, right, has 1 valence electron. What you're going to see is that the valence electrons are going to actually be shared between the hydrogens and the carbons. So by doing this, if they share it, right, you'll find that the hydrogens, because they're sharing its valence electron, and the carbon sharing one of its valence electrons, now the hydrogen has 2 valence electrons, because they're sharing in 4 cases. Now the carbon, it's sharing between the hydrogens 8 valence electrons. So it has achieved the octet rule. Now it's very stable. So covalent bonding occurs when you can achieve a full valence shell, and by doing so, you have a very stable atom. And then the line that you'll see between the bonding elements, each line represents a pair of valence electrons being shared. So if you look at this here, these 2 carbons, right, there's 2 lines between this. That means there's 4 valence electrons that are being shared between those carbon atoms. These 3 lines here, that means there's 6 valence electrons. So there's 3 pairs of valence electrons being shared between these atoms, the carbon atoms. It still has each carbon here when they bond like this, they still have eight valence electrons because you count them. There's 2 here, 6 here, so it's 8 valence electrons. This carbon's also sharing these 6 valence electrons too, and it's also sharing the valence electrons between the carbon and the hydrogen. Same here as well. Okay. If you have any questions, please ask me, send me an email, or ask me during class. I'll be glad to help you. Thank you. Bye.